morning, one and all. Welcome to the session 1 of 4th day of this FTP. I am Samprati Tupad, Department of ENC, VTU CPGS, Kalaburagi. It's my immense pleasure to introduce and welcome one of the eminent resource speaker of the session, Dr. Sanjeev Bonde sir. Sir pursued his PhD degree in Biomedical Engineering from Indian Institute of Technology, Bombay. Sir is currently serving as a professor at the Department of Electronics and Telecommunications, CPGS Institute of Engineering and Technology, Nanded, Maharashtra. He is a lifetime member of Indian Society for Technical Education. Sir was honored with Sushrut Award for the best paper in doctoral category of International Conference on Biomedical Engineering at Indian Institute of Science, Bangalore and Biomedical Society of India. Sir guided 20 MTech students and currently 4 PhD scholars are working under him. Sir has participated in various national conferences and Sir published 5 papers in referred journals and 8 papers in conferences. Sir organized and coordinated various short-term courses and also delivered 12 national level lecturers. So we are very pleasure to have you here, sir. I welcome you once again. Sir, now you can start the session, sir. Sir, hello.
Hello, sir. Hello, madam. I am audible now.
You can proceed, sir.
Proceed, sir.
Yes, sir. Yes, sir. So, a very good morning to all the participants. I think I am audible to everybody who has participated in this live session. Now, the today's topic that we have selected is why orthogonal transforms. So, before that, we should ask why transforms. Why do we require a transform? A very important thing in signal processing is the transform. But why we require transform? So, most of the time, all we are processing the information bearing signal in signal processing. Information bearing signal means every signal is containing some information and we want to extract the information from the signal. Now, whenever we want to extract the information in the form of maybe some codes or maybe some any other information based on probabilistic information, maybe deterministic information, maybe some stochastic information. So not necessary that all the time the information will be readily available or readily visible or readily extractable from the signal. Means the signal format most of the time is not suitable for getting the information from the signal. And therefore what exactly we are doing, we are changing representation of the signal. Means we simply change the representation of the signal and this change of representation is called as a transform. Means basically what we want to do, we want to change the representation of the signal. Means what do you mean by a transform? Transform is nothing but an alternate representation of the signal. Now, how this or why this alternate representation will require? Because we want to extract the required information. And the required information is not easily extractable in the current domain. And that's why we are changing the domain, that is changing the representation of the signal, which is generally called as a transform. So that in the transform domain, means in the change representation of the signal, basically whatever information that will require is easily available, easily visible or easily extractable. So when we are having such kind of transformation, various transformations in the signal processing, this transformation can be broadly classified into 2 categories. The first one is orthogonal transform and the second is non-orthogonal transform. Whereas the third category is also there, that is nearly orthogonal transform. But there are 2 major categories that will be considered orthogonal and non-orthogonal transforms. So basically we are preferring in signal processing the orthogonal transform. Why orthogonal transform? There are many advantages of the orthogonal transform. First thing is that when you are having an orthogonal transform, if suppose if you are taking the popular transform, that is Fourier transform or the Fourier based transform, Fourier series, Fourier transform, discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, various fast Fourier transform, whereas some Hotelling transform, KL transform, wavelet transform, all such kind of transformation, they are mostly orthogonal transformation. So when an orthogonal transformation is there, most of the time the kernel that has been used to transform the signal, kernel means the basis function that has been used for the transformation of the signal, they are orthogonal. And why they are orthogonal? Most of the time when they are orthogonal, and if they are complex, then simply invertible transform or invertible kernel will be simple. Means you can easily come back to the original domain by using simply the complex conjugate of the kernel. That is the first advantage. Second advantage is that you can directly compare the transform coefficients. Hello? Hello? Okay, shall we continue? Is the number?
Yeah, sir.
Is there any difficulty, sir?
No, sir.
Okay. So when the transform is orthogonal, and additional there is one term which is called the orthonormal transform. Means in addition to orthogonality, we are checking the norm of the basis functions. And when you are checking the norm of the basis function, and if the norm is unity, and if the basis functions are orthogonal, then generally you are calling it the orthonormal transformations. So when you are having an orthonormal transformation, or when you are having your kernel or the basis functions which are orthonormal for the set transform, then at that time you can directly compare the transform domain coefficients, which one is the bigger, which one is having its higher contribution, or hello. So these are the advantages of the orthonormal transformation. So instead of basically going, or most of the time it is implicitly assumed that the orthogonal transformations are also orthonormal transformations, because if the basis functions are not having a norm 1, then we can easily convert the basis functions to have a norm 1 or the norm unity. So I have selected for the today's presentation a very simple transform that everybody is knowing. Basically, we are discussing the Fourier series. And most of the time when we are studying in engineering, whether UG, PG, the Fourier series has been taught by the mathematician. And I am not blaming mathematicians, but because they are teaching the subject from the complete purity, and that's why they are more concerned with the mathematical terms, where as an engineer we are not considering, or we are not concerning the more mathematical terms of what is their interpretation in the signal processing, or what is their interpretation in engineering application. So we'll have another viewpoint for this Fourier series today. Now, how you are calculating the Fourier series? Next slide. So what is the definition of the Fourier series? You can represent any periodic, continuous time periodic signal or continuous time periodic function, and probably there are some Dirichlet conditions. So for some amount of time we'll set the Dirichlet conditions aside, because most of the signals in engineering applications, they follow these Dirichlet conditions. So if we are having such continuous time periodic signal or continuous time periodic function, we can easily represent it by using the harmonically related exponentials or harmonically related sines and cosines. Harmonically related means the frequency is harmonically related, integer multiple of the base frequency, that is n omega 0. So we are having the first function, that is cosine of n omega 0, and the second function sine of n omega 0, that everybody is knowing. So the Fourier series representation will be given by, that is f of t is equal to, where f of t is a continuous time periodic function, can be expressed as a linear combination. Means we are having a linear coefficient, that is a0 plus a1 into cosine of omega 0 t plus a2 into cosine of 2 times of omega 0 t, and so on up to the nth term of the cosine. So similarly, we are having the sine terms with the linear coefficients b1, b2 up to bn. Or concise notations, you can say that summation from n is equal to 0 to positive infinity, that is an cosine of n omega 0 and bn sine of n omega 0. Now what is our duty is to find out the values of this a0, an, bn, and decide the number of terms, because it's an infinite series. So depending on your application, how many terms are sufficient? Means we have to decide the value of n. That is, n number of terms are sufficient. So if the function or the series is convergent, or you can say that if the convergence is rapid, then few number of terms will be required. So everybody is knowing all this one. Now see how to interpret this Fourier series, because after completing the basic term of the mathematical representation of the Fourier series that everybody is knowing, we are raising number of questions, okay, and we'll try to answer those number of questions, which will give the another viewpoint of looking towards the Fourier series. Now what you are saying, that f of t is equal to summation of n is equal to 0 to infinity, that is an cosine of n omega 0 t plus bn sin of n omega 0 t. Whereas if you are having the substitution, our regular substitution, that is an cosine of an is equal to cn into cosine of theta n and bn is equal to cn sin of theta n. With this substitution, then we should be able to calculate cn is equal to under of an square plus bn square, and theta n will be equal to tan inverse of bn by an. And that's why if you are expanding this one by this substitution, if you are putting the value of an is equal to cn cosine of theta n and bn is equal to cn sin of theta n, it will be f of t is equal to summation of n is equal to 0 to infinity, that is cn cosine of theta n multiplied by cosine of n omega 0 to n. So similarly about the sine terms. So after trigonometric simplification, you will get the last equation, that is summation n is equal to 0 to infinity cn cosine of n omega 0 t minus theta n. Now how to interpret this one? We are knowing that this representation, that is f of t is equal to summation cn cosine of n omega 0 t minus theta n, and we are knowing that c1 is given by this one and theta n will be given by simply tan inverse of bn by an. And then afterwards, if I'll say here that cn is the amplitude spectrum and theta n will be the phase spectrum, okay, whereas n indicates as the nth harmonic. We are talking about the harmonic because our basic definition tells that you are breaking down the continuous time periodic functions into a number of sines and cosines, linear combinations of sines and cosines which are harmonically related. Okay, so after this one, if I'll say that if spectrum has been given, that is amplitude spectrum has been given to you as it has been shown on this PPT, and the phase spectrum has been given. So how you are interpreting this one? How the Fourier series has been interpreted? Suppose that C0 is having the amplitude 1, now C1 is having the amplitude 5, C2 is having the amplitude 3, and so on. And phase, when you are having n is equal to 0, there is no question of phase because the zeroth component will be simply average value, which is the real value. And then the first component is having minus pi by 2 plus pi by 2 and so on. So how we are interpreting this one? So this, now you are saying that C0 means a DC value which is having 1 volt. So in the first panel, a DC signal which is having 1 volt amplitude has been shown. Now the first harmonic which is having the amplitude phi and phase minus pi by 2 means it will be an inverted sign, that is negative sine waveform, which has been shown. So similarly, the second harmonic, which is having twice the frequency, the third harmonic, which is having thrice the frequency, and again phase. So such waveforms has been drawn. And when you are adding all such things, that is the linear combination of this one will give you your periodic signal. This is a simple interpretation of the Fourier series. And everybody is knowing this one. Now again, the same thing is that what all we are knowing that how to evaluate the Fourier coefficients. Now, how we are evaluating the Fourier coefficients? We are using a fixed procedure for evaluation of the Fourier coefficient. We are taking the integral over the period 0 to t basically. Now, we are, before going for that one, whatever the basis function that we have used for the computation of the Fourier series are the sines and cosines. So, they are orthogonal. So, these are the orthogonal properties of the sines and cosines. That is the basis function. So that is sine of m omega 0 t dt. If you are integrating over a period, then it will be 0 for all n. Then cosine, if you are integrating for any frequency, that is n omega 0 to dt integrated over 0 to t. That is for all n, but n should not be equal to 0, will gives you 0. So similarly, you are having this orthogonal properties of the sines and cosines. So sine multiplied by cosine whatever the values of n and m. For all m and n value, it integrated over the grade 0 to t will give you 0, and so on like this one. So I am not going into much more detail of this orthogonal properties because there are many things that has to be seen. And when you are having sine square and cos square, when m is equal to n in this equation, that is sine multiplied by sine and cosine multiplied by cosine. When m is equal to n, it becomes a square term, and when it will be squared, it will be evaluated to t by 2. Okay. Now see here that so f of t is equal to a0, that is our basic equation. Summation n is equal to 1 to infinity an cosine of n omega 0 t plus bn sine of n omega. So we want to evaluate the coefficients a0, an, and bn. We are using the fixed procedure. To this equation number 1, we are multiplying, that is the left hand side and right hand side of this equation by a suitable multiplying factor, and integrating both the sides from 0 to t, means over a period. This is the fixed procedure that we are using. So for determining a0, what we are doing here, for determining a0, this f of t dt means we are using the multiplying factor 1. So multiply the left side of this equation by 1 as well as right side of this equation by 1 and integrate it over 0 to t. And by using these orthogonal properties, then you can determine or you can simplify this integral. That is a0, that is equal to this a0 integral dt plus integral and summation an cosine of n omega 0 t, and similarly about this sinusoidal term, cosine term and sine term. So you are knowing that integrating cosine over 0 to t for any frequency when n is not equal to 0 will be 0. Means from the orthogonal properties, this integral will become 0. From orthogonal properties, this integral will be 0, and remaining term will be only a0. Okay. So this a0 multiplied by t will be equal to this left hand side, and that's why a0 will be equal to 1 over t integral from 0 to t f of t dt. That we are knowing. Okay. So similarly, you are finding out the value of an. So how you are finding out the value of an? Now here I am using, or we are generally using, the multiplying factor as cosine of m omega 0 t. Okay. So multiply to the basic equation of the Fourier series representation, that is both the sides, left hand side and right hand side, by this cosine of m omega 0 t, whereas m is any arbitrary integer, and integrate both the sides over a period. That's why you are able to see the equation on the screen, that is integration from 0 to t f of t cosine of m omega 0 t dt will be equal to, now the right hand side, complete right hand side multiplied by cosine function, that is cosine of m omega 0 t dt. Now when you are expanding this one and when you are using the orthogonal properties, see the second step, an cosine of m omega 0 t cosine of n omega 0 t, multiplication product. Okay. Whereas in the next plus, that is sine multiplied by cosine, so this will give you, this integration will gives you a 0 result, and that's why the first, that is a0 term and bn term, these two will become 0 and only cosine term is remaining. Now it will become now cos square when m is equal to n. If you are observing, this summation is varying from 1 to infinity. So during this course, n is having the value m at once, and therefore this term will be reduced to cos square, and cos square of m omega 0 t, when you are integrating from 0 to t, you are having this t by 2. Okay, and that's why it is finally coming am is equal to t by 2 or 2 by t integration 0 to t f of t cosine of n omega 0 t. This is the derivation for am. Now m is any arbitrary integer, that's why you can change m to n, and you can say that an is equal to 2 by t integration from 0 to t f of t cosine of m omega 0 t dt. So similarly, you can find out the value of bn. So for finding out the value of bn, you are using the multiplying factor sine of m omega 0 t and carrying out exactly the same procedure, and it comes out to be Bm will be equal to 2 by t, that is the last equation. Bm will be equal to 2 by t integration from f of t, or integration from 0 to t f of t sin of m omega 0 t dt. That's why I'll show you all the three equations, that is A0, An and Bn. First, the top three equations in the yellow color, that is A0, Am and Bm. And the last three equations, that is in the green color, that is A0, An and Bn. Simply m is replaced by n. Now up to this particular point, every engineer or every professional person who is working in the signal processing area, he is knowing the things. That A0 is given by this one, An is given by this particular formula, and by this particular formula. Now the question is that in signal processing, multiplication operation means multiplying a signal by a constant will not add any information to the signal. It is simply if the coefficient is more than or greater than 1, then it's amplification. If it is less than 1, then simply it is attenuation. So if the multiplying by a scalar will not add any information, that's a multiplication in signal processing is not considered the operation which will add some information to the signal. And that's why it is not so important, or it is not at all important. Multiplication is not at all important in case of a signal processing. That's why if you're observing these three, A0, An and Bn, they are also having some scalar multiplication coefficient, that is 1 by t, 2 by t and 2 by t. 1 by t and 2 by t. So if they are not so important, then what these coefficients are doing here in case of A0, An and B. So can we remove them? If we remove them, what will happen? Or if we put them, what is there? And the second is that while deriving this coefficient, that is A0, A and B, we have used the fifth procedure, that is multiplying the function by a suitable multiplying factor and in integrating it. Whereas what means the second factor been by suitable multiplier for A
360. 943.
ಸರ್ ಸಿಗುತ್ತೆ ಸರ್ ಅಕೌಂಟ್. ಕೆಲವರು ಹೇಳ್ತಾ ಅಂತಾರೆ, ಕೆಲವರು ಹೇಳ್ತಾ ಅಂತಾರೆ, ಕೆಲವರು ಅಂತ ಅಂತಾರೆ.
Sir, someone is having his mic on and it's creating disturbance to all the audience.
Z.
Hello.
ನಾವೆಲ್ಲರೂ ಫ್ರೆಂಡ್ಸ್.
Z.
Hello.
Z. Capital X.
ಎಲ್ಲರೂ ಅಷ್ಟೇ, ನಮ್ಮಡು ಅಂತಾರಷ್ಟೇ ಎಲ್ಲರೂ. ನಾನು ನಿಮಗೆ ಹೇಳ್ತಿಲ್ಲ, ಬೆನಿಫಿಟ್ ಮಾತ್ರ ಯಾರು ಕೊಡಂಗಿಲ್ಲ. ಬೆನಿಫಿಟ್ ಯಾರು ಕೇಳಂಗಿಲ್ಲ, ಬೆನಿಫಿಟ್ಸ್ ಮಾತ್ರ ನಮ್ಮ ಅಷ್ಟೇ ಎಲ್ಲರೂ ಅಷ್ಟೇ. ಏನ ಕೇಳಕ್ ಏನಿಲ್ಲ ಕೆಲ್ಸಿ.
Lot of crosstalk. Speaker is not heard.
Hello. Hello, is it audible now? Hello. Someone is having his mic on, and that's why creating disturbances for all the audience. Yeah. So now there are three questions that we have raised here. That is, why to have a fixed procedure, and why only this? That is having a multiplying factor and integrating it. The second thing is that how to select these coefficients, that is multiplying coefficients. That is, in case of A0 it will be 1, for AN it will be cosine of m omega 0 t, and for Bn it will be sine of m omega 0 t. Why? So for this one, we have to go to a concept of linear algebra, that is vector spaces and function spaces. So it is simple that a vector in three-dimensional space can be represented by, this is V is equal to AI plus Bj plus Ck, whereas I, J, and K are the basis. These are orthogonal in three orthogonal directions. Means this orthogonality can be confirmed by the dot product. That is, the dot product of Ij should be equal to dot product of Jk and will be equal to dot product of Ki and should be equal to 0. So when this mutual dot product is 0, you are saying that these three vectors are orthogonal. So orthogonality condition ensures that the representation of any vector using Ijk is unique. So this is the first thing. When you are having orthogonal basis functions, what is representation that you are getting will be unique representation. There will not be any redundancy. That is the first thing, it has to be noted. The second thing is that we call Ijk as a basis. These are the basis for the three-dimensional vector space. So by this means we say that any vector in R3, that is three-dimensional vector space, can be represented by using the three orthogonal vectors Ijk, that is the basis vector. So in other words, we can also call that I, J, and K, they span the three-dimensional vector space, to which we are calling as R3. So let V is equal to AI plus Bj plus Ck be a vector in R3. That is, it's a vector in three-dimensional vector space. So by continuously changing the values of A, B, C, that is the linear coefficients, we are going to get a new vector in R3. So the collection of all such vectors is nothing but the vector space which will be spanned by I, J, and K, that is three basis vectors. And mathematically, this can be given that is the span over, that is the span function, that is the span mathematical function, span over ABC, that is AI plus Bj plus Ck, and the closure of that one. Closure means which will also take the care of the boundary value problems. And this will be nothing but the member of R3, that is the three-dimensional vector space. Means these basis vectors, that is I, J, K, are spanning the three-dimensional vector space over A, B, and C. Now see here that the norm of a vector, this is the another definition that we are observing. The norm of a vector is nothing but the square root of the dot product of the vector with itself. That is square root of V into V. Means it will be under root of A square plus B square plus C square. This will give you the norm. There are many more definitions of the norms which are possible. But in our case, in signal processing, we are only considering this definition. So we are saying here that if this norm of a vector is unity, then we call this vector as a unity norm vector. Now, if given the vector that is V is equal to AI plus Bj plus Ck, we can simply tell that in which direction of Ijk the vector V is pointing by observing the coefficients of A, B, and C. Means C, what is the use of orthonormality? If these basis vectors are orthonormal, then by simply observing the values of A, B, C, you can find out the direction in which the vector V is pointing. If your basis functions are not orthonormal, then this is not possible. You cannot do this. Then given a vector V, how shall we find out the components? That is the value of A, B, and C. It is simple thing that you are doing here. See here that if V is equal to AI plus Bj plus Ck, how to find out the value of A? Simply multiply the vector to that particular basis, that is I. That is the dot product of V into I is nothing but A, because you are using here the orthogonal property. Means you are saying that this vector I with inner product I is 1, inner product of J and I is 0, inner product of K and I is 0. That's why this B and C terms will become 0, and simply you are saying that this is having a norm 1, that is the dot product of I with I is 1. That's why simply remaining A. That's why when you are multiplying the vector with a respective basis, you are getting its component. And this multiplication of the vector with a respective basis is called taking the projection on that basis. Means you are projecting here the vector V on I. You are projecting here vector V on J, and you are projecting here this vector V on K. Means for finding out the values of A, B, C, you are projecting the vector V on the respective basis, that is I, J, and K. This is the projection. Okay. Now, this is the same analogy. Means this is similar analogy is also present in case of the Fourier series. And for this one, we should see another terms, that is the function spaces, similar to the vector spaces. That is functions and function spaces. In vector space, we represent a vector in terms of orthogonal or orthonormal vectors, that to which we are calling as a basis. In Fourier series also is an extension of this idea. Fourier series is also an extension of this idea. Means we say that a function is expressed in terms of set of orthogonal functions. And which are the orthogonal functions? Sines and cosines. So to correlate with this idea in geometry, we now need to introduce the concept of orthogonality and norm with respect to the function. Means we are defining the terms orthogonality and norm with respect to the functions. We have done it with respect to vectors. Now we'll do it with respect to functions. So orthogonality of function depends on the multiplication and integration of the function. See here. Now, if there are two real functions, that is f1 and f2, then if you are integrating the functions from minus infinity to plus infinity, that is f1 multiplied by f2 dt, if this is equal to 0, then you are saying that the functions f1 and f2, they are orthogonal. So what you are doing here, you are first multiplying two functions point by point, means their point by point multiplication. Now you are summing up the area under the resulting product. You are integrating means you are summing the area under the product function. And if this area is 0, means the positive area will be equal to negative area, means the area which is above the x-axis and area below the x-axis. If they are same, then the summation will become 0. And that's why when it becomes 0, you are saying that f1 and f2, these two functions are orthogonal functions. Okay. So there is one additional term, that is, now what exactly you are doing, checking the orthogonality, means this is the similarity index functions. Means basically you are observing what is the similarity between f1 and f2. So now see here that if f1 and f2, these two functions are synchronous. Synchronous means if f1 is increasing, f2 is also increasing. If f2 is decreasing, f1 is also decreasing. Means if they are increasing, both are increasing. If they are decreasing, both are decreasing. If this situation happens, then we are saying that f1 and f2, they are varying in synchronous fashion. And if they are varying in synchronous fashion, then definitely this product function and the integration will have a higher value. Means if this integration is evaluated to the higher value, then you say that these two functions are similar. If this integration is evaluated to a very low value, means if f1 and f2, they are varying in asynchronous fashion. Asynchronous fashion means if f1 is increasing, f2 is decreasing. If f2 is decreasing, f1 is increasing. In this manner, then at that particular time, if they are perfectly varying in asynchronous manner, then definitely this integration will be 0. And when this integration will be 0, we are declaring them as an orthogonal function. Okay, means if they are varying asynchronous in perfect asynchronous manner, then you say that these two functions are orthogonal, and they are having a unity norm. Everyone, that is f1 and f2, they are having unity norm. Then you say that these two functions are orthonormal. See the same thing that we are clearly indicating here. Now see that orthonormal function. So two real functions f1 and f2 are said to be orthonormal if and only if, that is integral from infinity minus infinity to plus infinity f1 of 2 multiplied by f2 of 2 dt is equal to 0, and that is integration f1 of t, that is norm of f1 of t is equal to 1, and integral from f2 of t multiplied by f2 of t is equal to 1. Then both the functions, they are having a norm 1. If you are putting the value of I is equal to 1 and if you are putting the value of I is equal to 2. And in both the cases, if the integration is related to 1, then you are saying that the norm is equal to 1. So if the norm is equal to 1 and if they are orthogonal, then these two functions or this set of functions is called as the orthonormal functions. Now, these orthonormal functions can span the function space, means their linear combination will be a function space. Now we'll add the third function, that is u of t. It is a unit step function. It is also a periodic function. You can treat u of t as a periodic function with any period. Okay, so u of t, cosine of n omega 0 and sine of n omega 0t. These three functions is a set of orthogonal functions. See, check here. Now see, suppose u of t multiplied by sine of omega t. U of t is having the value 1. So integrating this will be equal to 0. Means u of t and sine of omega t both are orthogonal. So similarly, u of t into cosine of n omega t is also integral value with 0. That's why u of t, sine of omega t and cosine of omega t, these two functions are orthogonal. Now check the third function, that is generalizing sine cos. This also comes to 0. Okay, then sine multiplication of sine integrating it over 0 to t is also equal to 0, and cosine is also equal to 0. There are certain conditions that has to be satisfied. If these conditions has been satisfied, then this set of functions, that is u of t, sine of omega t and cosine of omega t, for any value of frequency, they are orthogonal functions. Okay, now if they are orthogonal, they can span the function space. And see here that, so the linear combination of these basis functions, that is a0 plus a1 cosine of omega 2 omega t plus a2 into cosine of 2 times of omega t plus so on. Now similarly the sine functions, b1 sine of omega t plus b2 sine of 2 times of omega t. This linear combinations of these three orthogonal functions will give you some function that is f of t, and which is belongs to L square, that is square integral function. It is a set of square integral. So L2R is equal to L2R. So what is L2R? L2R is nothing but a set of square integrable. So what is Fourier series? Fourier series is applicable only to the square integrable. Okay. Now what is your duty is to find out the values of a0, a1 and b0, b1. So how you are finding out these values? It is a similar thing that you are doing in the vectors. How you are finding out the elements of the component vectors? That is nothing but projecting the vector on the respective basis. So similarly here, when you want to find out a0, a1, a2, suppose I want to find out a1, then I am projecting this function f of t on cosine. When I want to find out b1, then I am projecting this particular function f of t on this sine function or sine omega t. So in the generalized term, we say that. See here. Now we address the problem of finding the coefficients a0, a1 and b0, b1 and so on like this. That is a and b. In vector algebra, orthonormality of the basis functions allowed us to find the component of the vector along a perpendicular or along a particular base by projecting the particular function on that particular base. That is the property, that is norm of I is equal to norm of j is equal to norm of k will be equal to 1. That is the unity norm. And their orthogonal properties, that is the dot product of ij, dot product of jk and dot product of ik is equal to 0. So these two properties will allow us to have a projection of that particular vector on that particular base and to give the value of the particular coefficient, that is A, B, or C. So a similar procedure has been employed here. See here that when you want to find out the function, the orthonormativity of two functions, that is f1 and f2 in 0 to t is this that we have already seen. This is orthogonal conditions, and remaining two are the norm conditions. Okay. So now check. We have seen that the basis in the cases of Fourier series or in the case of Fourier transformation, whatever it may be, it may be a Fourier series, or it may be a Fourier transform, or it may be a discrete time Fourier series, it may be a discrete time Fourier transform, it may be a discrete time Fourier transform, means any Fourier domain function. The basis are either exponential, and what do you mean by exponential? By using the Euler's identity, so sines and cosines. So sines and cosines are orthogonal, definitely, that we have seen, we have proved it, but we have not checked them for the orthonormality. Okay, so now check what is the norm of a unit step function. The norm of a unit step function is t. See where it has been calculated, integration u of t into u of t over 0 to t. So it comes out to be 2. T means the norm is not unity. See here, the norm of a sine function, that is sine n omega by 2. The norm is not unity. The norm is 2. It is not unity. Means basically u of t sine of omega t and cosine of omega t, or u of t sine of n omega 0 t, or cosine of n omega 0 t and sine of n omega 0 t. These are orthogonal functions, but they are not orthonormal functions. When they are not orthonormal functions, it is our duty to generate the orthonormal transform. So for generating the orthonormal transform, we will require the norm of the basis functions to be 1, whereas it is not 1. So we forcefully make the norm 1 or unity. And how to do it? In case of u of t, what is to be done? You are knowing that the norm of u of t is t, the norm of sine of omega t is t by 2, and the norm of cosine of omega t is t by 2. So multiply all the sines and cosines by under root of 2 by t, and u of t by under root of 1 by t. Multiply. So now we are multiplying. See here that. So under root of 2 by t sine of n omega t, under root of t by 2 sine of n omega t. Now this is unity norm. Okay. So this comes out to be 1. The norm we have calculated here, the norm is coming to be 1. So similarly, in case of the cosine function, now these are the normalized functions, that is cosine of n omega t multiplied by under root of 2 by t, a normalized function. So this normalized functions multiplied by itself and taking the integration will leads to 1. Means now these are having norm 1. So similarly, u of t is also having now norm 1, because u of t has been multiplied by under root of 1 by t. That's why the set of normalized basis of the Fourier series is given by under root of 1 by t, under root of 2 by t sine of omega t, under root of 2 by t cosine of omega t, under root of 2 by t sine of 2 omega t, and so on like this one. So basically, this is the set of orthogonal functions, orthonormal functions. Means sines and cosines are not orthonormal. They are orthogonal, but they are not orthonormal. So we are forcefully making them orthonormal. The norm of sines, cosines, and unit step functions to be unity. Okay, and now we are representing the Fourier series by using this normalized basis function like this. So this is the Fourier series by using the normalized basis function, that f of t is equal to a0 dash under root of 1 by t plus a1 dash under root of 2 by t cosine of omega t, and so on like this one. Okay. What is the difference between the previous representation of the Fourier series and this representation? In the previous representation, we are having only cosine of omega 0 t, cosine of 2 times of omega 0 t, sine of omega 0 t, sine of 2 times of omega 0 t. Means they are non line vector under root of 2 by t and under root of 1 by t. Okay, so now this is the Fourier series representation by using normalized basis. And now I want to find out I want to find out now the value of A0 dash, A1 dash, A2 dash, B1 dash, B2 dash, Bn dash. Normal. This is normalized Fourier series coefficient. The process remains same. And what is that process? Project the function. Now f of t, you have to project on this normalized base. Which is the normalized base? Suppose I want to calculate cosine of, or I want to calculate a1 dash. Then I have to project this f of t on this cosine. That is normalized cosine under root of 2 by t cosine of omega. Like this one. See here. Suppose we want to find out a1 or an dash. How are you finding out the an dash? So project the function f of t on the normalized base. What is the normalized base? Under root of 2 by t cosine of n omega t. So multiply the function f of t multiplied by under root of 2 by t cosine of n omega t. That is taking the function, multiplying with the normalized base and integrating over 0 to t. That is the projection. Means basically we are projecting the function on the respective base for getting the component. Which is the component? an dash. Okay. So an dash. So similarly, how you are calculating bn dash? It is simply 0 to t, means projecting the function f of t on the normalized base. Which is the normalized base? Under root of 2 by t sine of n omega t. Means equivalently bn dash will be equal to integration 0 to t f of t under root of 2 by t sine of n omega t dt. Okay. So similarly, a0 means what exactly you are doing? You are projecting the function on the normalized base now. The base is normal. Now put these values in the original equation. Okay. That is f of t. This is the original equation. a1 dash under root of 1 by t, a1 dash under root of 2 by t cosine of omega, and so on like this. Okay. And now here that. This is the basically how you are projecting it, and what you are getting the same thing, that is f of t, means both the sides of the equation, that is Fourier series representation, the basic equation, both the sides, left hand side and right hand side, has been multiplied by the normalized base under root of 2 by t cosine of n omega t and integrate it and use the orthogonal properties, and that's why an dash will be evaluated to f of t under root of 2 by t cosine of n omega t. So what exactly you are doing here? You are taking the projection. Okay. So now this an dash you are representing in terms of our a0, means now we are comparing this with our regular kind of Fourier series. Okay. Like this one. See that after applying the normalized coefficients, we substitute in Fourier series. Okay. So this is our Fourier series by using the normalized basis, that is f of t is equal to a0 dash under root of 1 by t. This is basically u of t. Okay, plus a1 dash under root of 2 by t cosine of omega t plus b1 dash under omega t. Now the second harmonic, the third harmonic, and the nth harmonic. So this is the nth harmonic term that I have represented here. an dash under root of 2 by t cosine of n omega t plus bn dash under root of 2 by t sine of n omega t. Now see here that if I'll have a substitution a0 dash multiplied by 1 by under root of t is equal to a0, means this is nothing but a0. So similarly a1 dash under root of 2 by t is nothing but a1. Similarly b1 dash multiplied by 2 by t is equal to b0 or bn or b1, like this one. Then you can see that when you are putting this substitution, basically a0 will comes out to be 1 by t under root of or 1 by t integration 0 to t f of t dt. So similarly, an dash under root of 2 by 2 is equal to an. If you are having this substitution, then an will be equal to under root of t by 2 an dash. So put the value of an dash. What is the value of an dash? So under root of 2 by t is a constant, as you are putting it as it is, and an dash is equal to under root of, under root of 2 by t multiplied by integration from 0 to t f of t multiplied by root 2 by t cosine of n omega t dt. Means this coefficient multiplied by the value of an dash. Okay, whereas an dash is nothing but the projection over the normalized base. So this root 2 by t will be a constant which will comes out of the integration and it becomes 2 by t integration 0 to t f of t cosine of n omega t. This is a regular representation. So similarly bn. Okay. So now you are writing our regular Fourier series, that is f of t is equal to a0 plus a1 cosine of omega t plus b1 sine of omega t and so on like this one. So whereas a0 is equal to, we are using this one. So now why this 1 by t, 2 by t is present here? So basically in case of a orthonormal transform will require the orthonormal basis functions, whereas sines and cosines they are orthogonal but not orthonormal, means their norm is not unity. Means basically in Fourier series we are using three basis functions, that is u of t, cosine and sine. All these three functions are mutually orthogonal, but they are not having a norm 1, means they cannot prove to be a set of orthonormal basis functions. So we are forcefully making them orthonormal by having some scalar coefficient. And the scalar coefficient that is required to make them orthonormal, this comes out of this integration, and that is nothing but 1 by t, 2 by t in case of an, and in case of bn it will be 2 by t. Okay. So in every transform in signal processing we are doing the same thing, means the basis functions that we are choosing most of the time they are orthogonal but not having the norm 1. So we are forcefully making the norm of the basis functions to be 1, to be unity, and we'll choose a suitable multiplying factor for doing that. And that's why this suitable multiplying factor will come out of the transformation equation. As in this particular case, it will be 1 by t and 2 by t. Okay. So it is just this multiplying factor. If we will remove it from there, then the resulting transformation will be only orthogonal transformation, but it will not be orthonormal transformation. And you cannot compare the coefficients, or you cannot draw the conclusion that if suppose A1 is having the higher amplitude than A2, then really it does mean that the amplitude or the energy content of the first or the power content of the first harmonic is greater than the second one. You cannot draw such conclusion. So for drawing such a conclusion, the basis functions need to be orthonormal, and if they are not orthonormal, you are forcefully making them orthonormal, and this forceful procedure will give you some coefficient, and that's why these coefficients are must here and you cannot remove them. This is the basic reason. Now we have asked three questions. The first question that we have asked is why we are having the fixed procedure. Because when you are having orthogonal transformation, for finding out the component will require the projection. And what is projection? Projection is nothing but multiplication of the two functions and integration. And that's why we are choosing the suitable multiplier and we are integrating them. This is the reason. Now the second question that has been raised, that what is coefficient, that is 1 by 2 and 2 by 2 are doing there. So they are forcefully making the basis functions to be orthonormal, so that you can easily compare and take the decision based on the amplitude of the transform coefficients in the transform domain. This is the second reason. Okay. So in any transform in engineering applications or signal processing applications, this is the truth. It means the bases are not orthonormal and we are making them forcefully orthonormal, means we are transforming the orthonormality conditions of the basis function onto the coefficient of the transform. Here we are transforming the orthonormality conditions of the basis functions onto the coefficient, that is A0, An and Bn, by choosing this 1 by 2, 2 by t and 2 by t. So this is a simple thing. Okay. Now we are doing in the regular practice, we are calculating the Fourier series question many more time, but we are not thinking, okay, what will happen if I will remove this 1 by t from here? What will happen if I remove this 2 by t from here? What is the purpose of this 1 by t there? What is the purpose of 2 by t there? Okay, so this is the purpose. And when you are looking towards any transformation in the signal processing, look from this viewpoint. Okay. Now, basically, we have taken it in a very faster manner on the PowerPoint presentation. If really sufficient time has been given and a blackboard and chalk has been given, then this will be very nicely explained and can be remembered. Okay, but because of the time constraints, we have used this one and we covered it in the faster manner. So basically, you will find this particular kind of treatment in many books. Okay, so try to see it, and I think now, thank you very much for bearing me for so much amount of time. And if you are having any questions, we can go for the questions or doubts. Hello. Hello. Hi, madam. Thank you, madam. Thank you, madam. Thank you. Thank you, madam. Have a great day. Thanks. अभिजित बंद करू कशाला लिहून मीटिंग